And I will share my screen and we will get at it. Hopefully. There we go. All right, beautiful. All right, so you will recall that we were discussing the transition from the microcanonical to the canonical ensemble. That is, we had a box that we divided into two subsystems, subsystem 1 and subsystem 2. So the whole system was microcanonical in the sense that no energy can enter or leave the box. So our walls here are completely impenetrable to anything and everything. However, our barrier here allowed the transfer of energy back and forth between the two subsystems. And so what we have shown is that the density of states of the entire system is related to the product of the density of states of each of the individual subsystems, like so. Okay. And that if we calculate probabilities of the energy having some specific value, then that is just the ratio of the density of states of the energies having that specific value. That is this. Divided by the entire density of states. Okay, now the fact that, so now we talked about how if we went through this analysis, what our answer would be that our solution, rho, would be a bell curve, a Gaussian that is centered around the most likely value, E star. The width of that Gaussian is going to be very, very narrow, and hence with high, very high probability, if you look at this system after it's settled down, the most likely state that you are going to find it in is the one at the maximum of this probability distribution. Okay, now when you calculate maxima of functions, the way that you do this, I guess I should use a total derivative. So what we were doing was this, and to find the maximum of this function, we find where this thing is equal to 0. So in other words, this relationship essentially allows us to determine what E star is going to be. All right, so we're taking derivatives of rho. Because rho is a product of two things, what we get from taking the derivative and the consequence of the chain rules, you wind up getting a sum of two things. All right, and so this condition led us to this statement. Like so, and evaluated at the maximum. Okay, and so the form of this function on each side of the equal sign compelled us to, or not compelled us, but just to make the math look prettier, it suggested that we define a new function, which we called S, that is related to the logarithm of the density of states. Okay. All right, so this function that we define simply by trying to make this expression look prettier is the entropy. Okay, and what this shows us is, so now if we substitute this back in to here, what we get is that this is true. That is the most likely state to find this thing in, your system in, is when the total entropy of the system is a maximum. Okay, so in other words, if you're interested in finding what the most likely equilibrium state of a system is, what you want to do is to write down an expression for its entropy using the density of states as we define right here. And then you look for the maxima of that function, and that'll tell you what the equilibrium steady state values are going to be. Okay, so the last thing we were doing before we left off on Wednesday was we were trying to relate our newly discovered entropy function to some things that we learned a quarter or so ago about classical thermodynamics. All right, so I asked you guys to remember these statements that hopefully you learned back in thermodynamics, specifically that 1 over the temperature in thermodynamics was defined to be the partial derivative of S with respect to E at constant volume and number of particles, that the pressure is equal to the negative derivative of E with respect to V. So this, I believe, is just a statement from the first law of thermodynamics. And that the chemical potential, which we'll spend plenty more time talking about later, so if you're not super comfortable with the chemical potential, hopefully you will be later. That this is simply how the energy of the system changes with the number of particles. That is, it's the energy required to add or remove a particle from the system. Okay, so I asked you to remember these few things. And another couple things we're going to need today are some just basic math formula that, again, hopefully you learned this in Calculus 3. All right, so let me write those down real fast. That is, if I have, so another thing to remember, and again, this is a pure math result, that if I have a function that is a function of multiple variables like this, okay, then I can form what's called the triple product rule. So the triple product rule is this, that if I take a whole bunch of derivatives of this thing, df dx, at constant y, I multiply by dx dy at constant f, and multiply that by dy df at constant x, that this is equal to -1. Neato. Okay, so this is hopefully something you've seen before. Okay, the other thing I ask you to recall from basic calculus is this silly little fact that if I take the derivative of a function with respect to one of its variables, whoops, let me do derivative of f with respect to x at constant y, that this is the same thing as 1 over the reciprocal. So instead of df dx, it's the same as 1 over dx df. Okay, which, you know, if you think about the derivative as like a fancy fraction, then this is obvious. But it turns out it's also true if you don't think about it in terms of a fancy fraction. Okay, so let's just remember these three things. Well, yeah, so these definitions of our temperature, pressure, and chemical potential from ancient thermodynamics, and these two silly little math expressions. And we are going to apply these to our grand canonical ensemble that we started talking about at the end of last lecture. Okay, so the grand canonical ensemble is where you allow essentially all the variables that describe your system, the energy, the volume, and the number of particles to vary. And so again, the way we did this was we took our micro canonical box, we split it up into a section of membrane that allows the energy to transfer back and forth, another like rubbery membrane that allows the volume to change by flexing back and forth like so. So by this thing, moving back and forth, what we're doing is we're essentially swapping volume between the two systems. And by including a little sieve-like region here, that allows particles to travel back and forth through the thing. Okay, and so when we allow this to happen, what happens is that the entropy, rather than just being a function of the energy, the entropy now is a function of all of these variables. And so if we're looking for what the equilibrium state of this system is, what we want to do is to write our entropy in terms of all three variables, and again, try to find where it is a maximum. Okay, and so the way we did this was, again, to assume that S is a function of E, V, and N, and then we take the differential of it. And just from the chain rule, what the differential gives you is this. So this is essentially what we wound up with at the end of last lecture. Okay, dE. And then when we allow the volume to vary, we get ds dV1, constant energy and number of particles, minus ds dV2, and energy and number of particles, dV. And then we let n float around. And when we let n float around, we get ds dN1 at constant E and V, minus ds dN2, constant E and V, dN. Okay, and again, we're looking for the maxima of this function, and hence what we do is we take the differential and set it equal to 0. Just like, so now the E, V, and N are independent variables of one another. And consequently, for this whole function to equal 0, what has to happen is that the coefficient of each one of the differentials also has to equal 0. So in other words, this quantity right here has to equal 0. This quantity right here has to equal 0. And this quantity right here has to equal 0. And so now what we left off with from last lecture was that when we look at this first one, the blue one, this is essentially the same condition that we derived looking at the canonical ensemble. So in other words, what this blue one tells us is that the maximum in the entropy, that is the most probable state to find your system in, is when the two temperatures of your system are equal. Okay, so now let's talk about what these other two give us. I'm going to use the darker green because that's going to hurt the eyeballs with the bright green. All right, so now let's talk about the second one. All right, so the second one says that this is true, that the partial derivative of S with respect to volume, whoops, keeping the energy and number of particles constant, minus, whoops, let's not do that, ds dv2, E and N, this should also equal 0. Okay, so now what we're going to do is to apply these basic mathematical relationships that I warned you about earlier. All right, so what we're going to do is we're going to, so using the triple product rule, we can say that this is the case, that ds dv, constant E and N, times dv de, at constant S and N, times dE ds at constant V and N, this has to equal -1. Okay? Now, this doohickey right here, dE ds, that is, if you look right here, that's the temperature, right? So this last one, this is just the temperature. The second one, the dVdE, I'm going to use this trick on it. So I'm going to take dVdE and flip it upside down and make this into 1 over dE dV. Okay? And then the first term I'm going to just leave by itself. Or leave it the way it originally was. So like so. Okay. Now, and this is again equal to -1. So this is just the product rule. All right. Okay, so now what I'm going to do is to take this funny looking thing and just move it over to the other side. All right, so what I get is ds dv at constant energy and number of particles times the temperature is equal to dE dV, excuse me, minus dE dV at constant S and N. Okay, all right, so everybody cool so far? We go back up here. Oh, look, dE dV minus dE dV, that's the pressure. Okay, so in other words, what we get from our triple product rule is that the pressure over the temperature is equal to ds dV. Okay, so this is from the triple product rule. We know that the temperatures of the two, so now what we do is we take this expression and we plug it back here into this relationship between the two subsystems that we derive from taking this differential. And so in other words, we get that the pressure over the temperature of one subsystem minus the pressure over the temperature of the other one has to equal 0. We know the two temperatures are already equal from the previous thing we talked about. And hence we also find that the two pressures are equal at equilibrium. Okay, so at equilibrium, temperature on both sides is going to be the same. Pressure on both sides is going to be the same. All right, now, so that just leaves this last one, the purple. All right, so the purple gave us that ds dN1 at constant E and V minus ds dN2 at constant E and V is equal to 0. Now, I'm not going to go through the whole thing. The argument is the procedure is exactly identical to what we just did for the green one here for the pressure. Okay, so you just go back and you do exactly the same business again. All right, you'll get something that looks like this. Okay, again, if you compare it to our relationships from classical thermodynamics, and what that last condition is going to give you if you repeat this whole business again is that the chemical potentials on both sides are going to have to be the same. Okay, so the most likely state of your system, that is the state it will occupy at equilibrium, is the one that maximizes the entropy. And the state which maximizes the entropy, as we just showed, is where the temperatures of the two subsystems are equal, the pressure of the two subsystems are equal. No, I'm not going to use that finger. The chemical potentials of the two subsystems are equal. All right, so that's entropy. So entropy, super fundamental. You just calculate your density of states, take the logarithm, multiply by a constant, that gives you your entropy. And then simply by maximizing this function, you can determine essentially what the most probable states of your system are going to be. Pretty cool. Okay, so now, this whole discussion so far has been rather abstract, right? So now that we know about entropy and how to use it, and so once we have entropy, oh, so I wanted one more thing. So again, if you go through this whole business here, the relationship that you're going to get is that minus mu over T is equal to ds dN. Okay, we're going to need that shortly. All right, so now what we're going to do is to take all this machinery that we've put together That is, we calculate the entropy, and then by taking derivatives of the entropy, we can determine what the chemical potential, what the pressure, and what the temperature of the system are. So we calculate the entropy, take a derivative with respect to N, that'll give you the chemical potential. You calculate the entropy, you take the derivative with respect to V, that'll give you the pressure. You calculate the entropy and you take the derivative with respect to E, and that'll give you the temperature. Okay, so we're going to take all this machinery we just put together and apply it to a specific system. Can you guess what that specific system is going to be? The ideal gas. All right, so let's go back to our good buddy, the ideal gas. So let's talk about temperature and entropy of the ideal gas. Specifically, the well, let's not say that. Let's not constrain ourselves, shall we? So temperature and entropy of the ideal gas. Let me make sure I have the right notes. All right, so now, a few lectures ago, we started talking about the ideal gas within the microcanonical ensemble. And we showed you. Okay, so we started talking about how do you calculate the density of states, omega of E, for the microcanonical ideal gas. And what we showed, one of the very first things we talked about was that it was equal to this, right? So you take all of the momenta of your individual atoms, you take all of the positions of your individual atoms, you integrate over all possible values of that, and that'll tell you the density of states. Okay, and then we went through this whole business to do this explicitly for the ideal gas. And what we got was this. So we got that omega of E was equal to 3nm times pi to the 3n over 2 times r to the 3n minus 2 divided by 3n over 2 factorial, where r is equal to the square root of 2me. All right, and you'll remember that the way that we got this was by looking at, in momentum space, we had no, that's not what we did. We had px, py, pz. We had a cool sphere. We kicked the radius of this sphere out by a little bit. And what this expression is the volume of this shell in our momentum phase space. Everybody remembers this? Excellent. So we got this from looking at the number of states available to us in momentum space, right? We haven't talked at all yet about positions. So I was telling a little bit of a fib to you. This is only part. So this expression here, that's only part of the density of states. Specifically, this is the density of momentum states. Right, so I should, to be more precise, I should call this something like omega sub p of E. All right, so this tells us all of the momentum states that are available to us. We have not talked at all about configuration. So what are called configuration states? Okay, so in other words, what we've done is that if we started here, all we've done so far is to evaluate this part of the integral. We haven't evaluated anything to do with position yet. Okay, so in order to get the complete density of states, we have to take our density of momentum states and multiply by the density of configuration states. Okay, so does that make sense? All right, good. So let's talk about how to calculate the density of configuration state. And configuration states just means that it's just this way to physically, spatially, or distribute all of the atoms and molecules in your box. Okay, so now how are we going to do this? Okay, so in other words, what we want to evaluate is this. We want to calculate our density of configuration states. Okay, and this is going to be related to this integral. Okay. So now, again, let's say we have a box of volume V. And let's just talk about a single particle. Okay, so again, these Q's here are simply the spatial coordinates of the molecules in our box. So if we only have one molecule, then this dq is simply the spatial coordinates of that one molecule. Okay, so in other words, for a single particle, which I'll write like this, this is simply dx, dy, dz, integrated over all possible values. Okay, so what are the all possible values? So all the possible values of x and y and z are all the values that fit inside the box, right? So in other words, when we evaluate this integral, what we are going to get is the width of the box times the height of the box times the depth of the box. So in other words, this is going to be v. Okay, does that make sense? All right, cool. So now, if I have more than one particle, again, we're talking about an ideal gas, so the particles essentially can't see each other at all. So even if there's two particles in the box that are bouncing around, those two particles are going to behave essentially like, they're going to behave exactly the same way as if there was just one particle, just there's going to be two of them. So in other words, if I have two particles, my density of configuration states is simply going to be V times V, that is V squared. So now making the generalization that we have n particles, omega of the configuration states is simply V to the n, piece of cake. Okay, does that make sense? I hope. Okay, cool. So to get the total density of states for our ideal gas, we take our density of configuration states times our density of momentum states. Our density of configuration states is simply V to the n. And our density of momentum states is this thing that we derived last week, I think. Last week or Monday or something. I don't remember exactly. So it's just this thing. It's 3nm times pi to the 3n over 2 times 2me to the 3n over 2 divided by 2me divided by 3n over 2 factorial. Okay, so now what I'm doing to get this from this statement that I gave you earlier is I'm substituting in that r is equal to the square root of 2me. I'm taking this minus 2 in the exponent here, and so that gives me a factor of 1 over 2me. So that's this thing. Okay, so this over 2me is coming from right there. Okay? And so what you get is this. Okay, so this is the density of states of our ideal gas. Okay, so now, let me rearrange this a little bit. Let me write this in the following way. And again, all I'm doing is just I'm grouping things together here. So it's just exactly the same thing. I'm just going to group some things together in the following way. So I got v to the n pi to the 3n over 2 times 2me to the 3n over 2 divided by 3n over 2 factorial times 3n over 2e. Okay. All right, so now, everybody cool? All right, cool. So now what we want, so this is our density of states. Now what I want to do is to write down an expression for the entropy. So now, let's write down the entropy. Now the entropy is simply, we take this expression for our density of states and we take the logarithm of it. Okay, so now we've got the logarithm, we're going to take the logarithm of the product of a whole bunch of things. Okay, and hopefully you remember that if I take the logarithm of a product of a whole bunch of things like so, that is equal to the sum of logarithms. Okay? All right, so what I'm going to do is I'm going to take this expression for omega of e, and I'm going to plug it in right here and take the logarithm of it. And when I do that, I am going to get the following. All right, so we get that the entropy as a function of the energy is equal to kb log. Okay, and what I'm going to take this part. So I get v to the n pi to the 3n over 2 times 2me to the 3n over 2 divided by 3n over 2 factorial plus this part. Okay, so I get that the entropy is this logarithm here plus this logarithm here. All right, so now I'm going to look into the future because again, they don't make just anybody a professor, only people who can see into the future. Okay, and so I'm going to tell you that we get to the point where we calculate what the energy of our ideal gas is going to be. We are going to get that the energy is directly proportional to the number of particles. In other words, this thing is going to be a constant. Okay, so what we're going to have is some complicated function plus a constant. And because what we're going to be interested in doing is taking derivatives of the entropy, derivatives of constants are going to give you 0 anyway. And hence, in the future, I am going to just neglect this term. All right, so now somebody had a question. Oh, a bunch of people have questions. What do we got? My dreams ruined. Oh, I'm sorry to hear that, Indy. Oh, it's because you can't see into the future. Don't worry, young lad, it'll come. Just drink enough Mountain Dew and eat enough Doritos, and eventually, it's like the spice melange, right? You'll eventually, you go through the trials out in the desert, and then you'll be able to see into the future. Don't worry about it. All right, so again, this term is just a constant, and so we're going to forget about it. And consequently, we're just going to work with this thing going forward, okay? Okay. All right, so now, again, we got a product of a whole bunch of crap. And so again, we can take the logarithm of the product of a bunch of crap and spread it out into the sum of logarithms of a bunch of crap. Okay, and so we get that the entropy is equal to, again, I'm going to, so this first term here, I get the logarithm of v to the n. The logarithm of something to an exponent, you can just pull the exponent out in front, and so I get n log v. Okay, the next bit, I get 3n kb over 2 log 2me. Okay, so that's coming from, oh, sorry, I dropped a pi, 2 pi. So that's coming from here. Okay, and then the last term is this logarithm of a factorial. All right, everybody good? All right, so now this is the expression of the entropy for an ideal gas. So now we want to start calculating things like, what is the temperature of this ideal gas? What is the pressure of this ideal gas? What is the chemical potential of this ideal gas? And the way that you do this is you take this expression for your entropy and you just start taking derivatives. All right, so for example, we know that 1 over the temperature should be equal to the derivative of the entropy with respect to energy at constant volume and particle number. So you just take this expression, you differentiate with respect to energy. So with respect to energy, this first term is a constant, so that'll go to 0. The last term is a constant, that'll go to 0. So the only one we got to worry about is, I think we did blue earlier, so we got to worry about this silly little monkey right here. All right, and so when we do this, we get a bunch of constants, 3n kb over 2. We, when you take the derivative of the logarithm, you get 1 over the argument of the logarithm. So we get 1 over 2 pi me. And then you got to take the derivative. The chain rule tells us you got to take the derivative of the argument of the logarithm, and so you get 2 pi m. Okay, so 2 pi m, that cancels. And so what I get is that 1 over the temperature is equal to 3n kb over 2e. Okay. All right, now, so that's how we get the temperature. Now let's get the pressure. So the pressure, I believe I wrote in green earlier. So the relationship we just derived from looking at the differential of the entropy was that the pressure over the temperature should be given by the derivative of the entropy with respect to volume at constant energy and number of particles. Okay, so we go back up here to our big hairy expression for the entropy. And for this one, so now we're looking for terms that have volume in them, yes? So this, no volume here. So that goes to 0. No volume here. That goes to 0. Here's a big fat V right here. All right, so when we take the derivative with respect to volume, we only have to worry about this first term. And oh man, again, it's so easy, even a biologist could do it. All right, so you take the derivative of S with respect to V, and you get N times KB, and then you get 1 over V, right? What's that? Well, so now let me just rearrange these things a bit. So we get the pressure times the volume is equal to the number of particles times Boltzmann's constant times T. Yes, it looks like some kind of gas, which maybe is ideal, right? So this is the ideal gas law. So this is kind of nuts, right? So we started out, where we started here was we started with a box that's full of a bunch of balls. Those balls have momentum p squared over 2m. And simply by counting the possible states available to a number of balls with kinetic energy p squared over 2m, we have derived the ideal gas law. Kablooey. Pretty amazing. Okay, so this gives us the ideal gas law. So this is our equation of state. Maybe you'll remember that on the very first day of this class, I told you that the goal of statistical mechanics was to start with a microscopic description of the motion of the individual components of your system. And you apply statistics to that in order to derive the macroscopic equation of state of your system. Ta-da! We just did it. Okay, so we started with a box full of balls. Each of those balls has momentum p, kinetic energy p squared over 2m. We derived macroscopic ideal gas law, PV equals nkt. Okay. All right, now, is there something else I want to do? Yes, let's go back. Let's look at this thing a little bit further. All right, so when we took the derivative with respect to energy, we got this relationship. 1 over the temperature is 3nk over 2e. If we just rearrange that a little bit, we get that kT, that's the energy of the gas, is 2e over 3n. Okay, or in other words, the energy is 3/2 nkt. Which, hey, maybe that looks familiar to you too from thermodynamics, I believe. Yes? All right, so we just derived that the energy is equal to 3/2 nkt. You also notice that the energy, as we said, is directly proportional to the number of particles. That's why this thingy right here was going to give us a constant, right? And the Quisatz-Heterach. All right. All right, cool, right? So we start with our microscopic description of each of the individual balls of our ideal gas. We calculate the number of states available to such a collection of balls. We just take the logarithm of that number of states. That tells us the entropy. Once we have the entropy, we just take some derivatives, and that gives us temperature, energy, pressure. Okay, so we get the ideal gas law out of it. Amazing. So that's essentially the entirety of statistical mechanics right there. Okay, so these are the kinds of things that you do is you calculate the number of states, you find some expression for the energy or the entropy, and then you start taking derivatives, and that allows you to calculate things like equation of states, pressure, temperature, energy, so on and so forth. Okay, so now it's time for us to correct a few misconceptions, or not misconceptions, let's call them what they are, lies that I've told you so far. They're not lies, they're simplifications. Simplifications. All right, so now let's talk about refinements. All right, specifically refinements to this expression. So we said we calculate the density of states using this. Okay, so now it turns out there's some things about this which are less than ideal. And so now what we want to do is to make a few modifications to this expression that will make it work better. All right, so first of all, so the first refinement we're going to make is notice that if you, so this has dimensions of length, right? It's just spatial coordinates. This has units of momentum, right? So in other words, omega, and just to be even more explicit, when the explicit formula we got for omega for an ideal gas was this: v to the n pi to the 3n over 2, 2me to the 3n over 2 over 3n over 2 factorial. Okay, now you look at this thing, it is not unitless, okay? So again, this is a density of states, so we're just counting states. You would not expect a density of states of a pure number to have units. This thing has units. Okay, specifically, this thing has units of length times momentum. To the 3n. That's bad. You don't want a density of a pure number to have units. And this has other really weird consequences. So for example, if I were to change the units that I'm measuring the momentum in, or the units that I'm measuring the length in, that would change my calculation for the density of states. That doesn't really make any damn sense. Okay, and so what we want to do is essentially to take this expression that we have been using and divide it by some constant, which also has units of length and momentum, such that we can give ourselves a dimensionless density of states. So now you go and you flip through all of your fundamental physics constants, and you see which fundamental physics constants have units of length times momentum. And it turns out that H, Planck's constant, has units of length times momentum. Okay. And so it turns out that if we, instead of calculating the density of states as we did before, if we calculate it as 1 over h to the 3n, okay, and yeah, this thing technically should be out there too, that will give us a dimensionless number. And so now it turns out that once we start talking about quantum mechanics, that this is going to actually make quite a bit of sense. Okay, so by dividing by Planck's constant to the 3n, what that is going to do is actually set the entropy equals 0 state when the absolute temperature equals 0. So in other words, by what this does by dividing by Planck's constant is it sets the 0 of entropy also at the 0 of temperature, which is good. Okay, so that's one refinement we're going to make, is in the future we are going to divide our densities of states by h to the 3n. Okay, the second thing we are going to do is what's called the Gibbs factor. Not the Gibbs from the Bee Gees, the Gibbs from the 19th century, the smart one, not the one who's, you can tell by the way he walks and talks that he's a ladies' man. No, time does. I don't remember how the song goes. Okay, but so the Gibbs factor. So we're running out of time. We only got about 1 minute left. So I'm going to tell you what the Gibbs factor is. Okay, so the Gibbs factor is another factor of 1 over n factorial. And so what we're going to do in order to calculate the density of states is we're going to, what we're going to do in the future is just this: h to the 3n times n factorial times dp dq. Okay, and so where this extra factor of n factorial is going to come from, we'll talk about it more on Monday, but what it comes from is the fact that our particles are more or less, it's what's called undistinguished. So in principle, they are distinguishable, but we have not been able, we haven't put any labels on each of our individual atoms and molecules. And because there are no labels on them, we'll talk about it in more detail on Monday. But what we're going to wind up doing is calculating our density of states like this. Okay, so Monday we're going to talk about the Gibbs factor in a bit more detail. And then we're going to start doing some more. I think actually on Monday we're going to apply this to black holes. Awesome. Just to see what happens when you talk about black holes. All right, cool. So any questions about anything? All right, very good. Then I guess we're done. Have a good weekend. I'll see you guys on Monday.